Hi folks, in this video we're going to talk about magnetism and we're going to introduce the magnetism aspect of what we've been calling up until this point electromagnetic fields. So we've looked at electric fields and then as the word would suggest there's a magnetic component to this as well. So this is all going to be about magnetic fields and looking at what happens with them. Okay, so we'll jump straight in and we'll go to the learning intentions and we'll have a look and see exactly what we need to have. So here we go, we're looking at the set of learning intentions and we're going to start here with 13.15. So here it says, I know that electrons are in motion around atomic nuclei and individually produce a magnetic field, or a magnetic effect. I know that certain materials exhibit a magnetic effect called ferromagnetism. And here we can have something, I'll talk about something called domains, and then the domains or the magnetic dipoles can align, which will eventually make a magnet. We can sketch magnetic field patterns around, so we'll look at a bar magnet, a solenoid. A solenoid, of course, is just a coil of wire with a core in it, an iron core, and the magnetic field around the Earth. Then we're going to compare the three types of field that we've come across so far, which is, of course, gravitational fields, electric fields, and magnetic fields. And that's what this lesson will be about. Okay, so let's just jump straight in. So the majority of what I'm going to be talking about today is going to be covered in the course notes on pages 16 and 17 about magnetic fields. And we can see here that this is something that should be instantly familiar to all of you, is that is a magnetic field pattern around a bar magnet. And whether you've done this before, you've seen it being done, what we would generally do is you would take a bar magnet, like so, and it would either have north or south written on it, or sometimes they're coloured there. And you would stick a card or a piece of paper over the top of this, and then you get some iron filings, and iron filings will be in like a salt shaker, a pepper shaker, and then you just sprinkle the iron filings on top of there, and you'll get a really nice clear field pattern. And what it will be is it will come out a bit like this. Oops. Really want to avoid them crossing at all, because as with electric fields, what we're going to see is that the spacing indicates the relative field strength. So the closer that they are, the stronger the magnetic field. So if we have a touching line, then that's obviously not very good. But the direction of the field would always point from north to south, and so that's the direction that a compass needle would point if placed in that field. And so here we're having everything pointing south, comes out of the North Pole like so, and then this could be continued into around here. And I won't do it too much more than this, I'm sure you get the idea by now. So some things here, obviously I've already said that the direction of the arrows is the way that a compass needle would point. The field is three-dimensional, so although what we're doing is in this experiment we're sprinkling iron filings onto a sheet of paper which will be two-dimensional, but the magnetic field will extend in a three-dimensional, I don't know what you would call this, there'll be some name for it, but so a three-dimensional pattern around, and we have our north side of the magnet, and we have our south side of the magnet, like so. Okay, so what actually is a magnet, and how is it caused? Well, there's a number of different ways that I could start with this, but what I'll do is I'm going to sort of change the order here, that we have our notes, and we have what is a magnet down here, but then we've got this thing called Ørsted's experiment. So Ørsted's experiment, named after the gentleman Hans Christian Ørsted, is a Danish physicist who did an experiment, and we would have done this in class, that and what he noticed is that he had a wire, and he was passed a current through this wire, so we'll just call that I. And so obviously a current is I Q over T. So it's the movement of charge per unit of time. So the charge obviously is contained within the electrons. The electrons are contain the charges, and as the electrons are moving through the wire, there's going to be a current flowing. And what he did was he took a wire, and let's try and do this. It's not a very good drawing of it. I can see this, but it should be hidden here. So that's under. Yeah, you get the idea, right? Okay, and so he had a wire with a current going through it, got a hole in the card, and then he placed some little magnets, some little what we would call button compasses. And these button compasses, when we turn off the current, so no current is flowing, it's just a wire, it's not connected up, then the compasses are all going to point to north. They're all going to point up in this direction. Okay, now as soon as he turned on the current and allowed current to flow through there, then what he noticed is that, I'm just going to draw it again. We'll be back in a minute. There we go. The power of TV, we now have an instant drawing. So before there was no current, scribble that out, there's no current, and they're all going to point towards north. As soon as the current started flowing through the wire, he noticed that the needles of the compasses realigned themselves. And what they did is they started to move, well, they didn't start to move, they moved to form a circular path around this wire. And so obviously the conclusion of this is that when current flows through when current flows through a wire, there is a magnetic field that was obviously stronger than the Earth's magnetic field, that had been created around the wire. And if we're going to look at, how do we see this? So if we've got our left hand here, it's something called the left hand grip rule. And so left hand like this, just curl it round, and your thumb will indicate the direction of current flow. And so if we've got here, our thumb is going up, and the curve of our fingers coming round is going to be the direction of the magnetic field. And so if we have our current going up like this, then we're going to have a curved round of the magnetic field, like so. And so when you pass charge through a wire, or a current through a wire, or a charge moves indeed, you will get the creation of a magnetic field. And so that's as simple as I can possibly put it. The cause for a magnetic field is the movement of charge. And if we go and look again in course notes, so we have three types of field. Your gravitational field, which is going to be created when an object has mass. Any object that has a mass will have a magnetic field around it, and just having mass, so you're not doing anything with the mass. Now, electric field, and what we've been looking at in this topic so far, is that you have a charge. It can be a positive charge, it can be a negative charge, it doesn't matter. The simple presence of charge will create an electric field around it. However, if you have a charge that is moving, then that will also create a magnetic field. And so it's the movement of charge which will create a magnetic field. But wait a minute, what happens with a permanent magnet? So you can have a bar magnet that was in here. So how does that work? All right, well, if we just take our bar magnet, and our bar magnet is going to be made of a ferromagnetic material. And so ferromagnetic materials, let's see, so we'll have iron, cobalt, nickel, so these three materials will be able to display ferromagnetic properties. You'll also get some what we would call rare earth magnets. Neodymium being the most well-known one. The neodymium magnet is an alloy made with neodymium and iron and other things as well. And these rare earth magnets can be incredibly powerful, but these can all be made into so first of all electromagnets, but also permanent magnets. And so first of all, well, how can you make something magnetic? You'll obviously know that if you have hang on. So what I've got is I've just got two little Torx headed bits for a screwdriver, and so what we can see is that they're made of iron or steel, and on their own they are in theory not magnetic at all. There is some degree of magnetism just because of where they are in the toolkit, but they're not magnetic. And so these are unmagnetized, albeit a ferromagnetic material. If I connect into my screwdriver, there is a magnet inside the screwdriver, and so as soon as the magnet comes into contact with the ferromagnetic material, then this now in theory should become magnetized, and it will indeed become magnetized. And if I separate it from the magnet, let's see if you can actually see what I'm doing here, then as soon as I take it out from here, it should just fall off, like so. And then it is no longer magnetized. So what's going on with all of this? Well, you will have an atom. So you've got your individual atom, and your atom, the nucleus is going to be here, and let's just say that we have one electron, and your electron is going to be orbiting around the nucleus. Let's just say that it's going to be doing that. Now, as you have a charge that is moving, then you will get a microscopic, I mean it's infinitesimally small, but nevertheless you get a magnetic field around each individual atom, or each individual nucleus. The movement of electrons around the nucleus will create a magnetic field for that atom. And so each individual atom will create its own magnetic field. And specific to ferromagnetic materials, what you'll have is these things that will sort of form, and we'll call them domains. And these are regions within the material where the spins of electrons line up. So as the spins of all the individual atoms, they all line up, and so you will get a region within that material that has a definite magnetic field. The strengths of the magnetic fields will add up and create a noticeable magnetic field. But they're all pointing in random directions. And what you'll find is that all these domains will eventually cancel each other out, and there will be no net magnetic field around. Okay, so this is a ferromagnetic material. It has its domains, and in its normal state, it's not magnetic. It's not magnetized. And so, if you remember back to the learning intentions, it's talking about magnetic dipoles, and so a dipole really is this. So you have your closed loop where you have your two poles. A magnet can't exist on its own. That doesn't make any sense. No. Yeah, you can have a point charge, and you can have a charge which is, if it's a positive charge, it'll be an electric field, and it's an isolated thing. Whereas a magnet must be a dipole, so you must have a north and a south component to it, and it must sort of have this sort of closed loop thing around it. So that's what a dipole is. It's like the north and south closed point. And so each of these, what the learning intentions are referring to, that each of these are the ferromagnetic dipoles. And so in this, what I would call a domain, so in this domain, the dipole would kind of be extending, if I just get this, it would be extending around in a closed loop from there to there. And you would get all of these magnetic dipoles. Okay, so this is an unmagnetized material, and it's not aligned. Now, you can do one of two things to this. I'm just going to do this really quickly because you sort of get the idea. So your magnetic material, your ferromagnetic material, now you can do one of two things. You can either bring a permanent magnet close. And so let's just say you'll get your permanent magnet, and you bring your permanent magnet close. Or you can wrap a coil of wire around it. So you can put this coil of wire, or you can wrap a coil of wire around it and pass a current through it. And so if we're gonna make an electromagnet, so you pass a current through a coil of wire that has this as a core, then what happens is that all of the domains, all of the individual dipoles, will align themselves in the same direction. Like so. Okay. Now there's a couple of different things that you can do with this. So you can turn it on, you can turn it off. So sorry, you can turn it off, and the dipoles, the domains, will then just realign randomly again, and it will no longer be magnetized. But what you can do, you can also there's certain things that you can do, like you can take your ferromagnetic material and you can strike it. You can place it in a very, very strong magnetic field. You can pass a very, very large current, so you can have it experience a very, very strong magnetic field, which will then impart permanent magnetism into this material. And so now you can create this as a permanent magnet. And you'll have noticed that you saw when I had the Torx screwdriver bits earlier, that although they were unmagnetized, just through age and through use of bringing them into contact with the magnet and the screwdriver head, it started to impart the permanent magnetism into that. And yeah, and you can go the other way as well. You can take your permanent magnet and you can heat it up, and if you heat it up to a certain temperature, I can't quite remember what they call it. It's like a Curie level or something. But heat it up to a certain temperature, and it will lose its permanent magnetism, and the domains will then realign again. So we have our bar magnetic field around here. Now let's just have a little look at a solenoid or an electromagnet. And so for our solenoid, we're going to take an iron core. And we're going to wrap a wire around this iron core. So if you pass a current through this wire, so let's say the current is going to go in that direction, you're going to have it moving around like this. Then what you'll have is that you'll have a magnetic field, and that magnetic field will be created here, and so you'll get a magnetic field that is like this, and of course that is going to then be very similar to the field around a bar magnet. Lines coming in like this, and eventually we'll have like so. So what about the Earth? Now the Earth, well, here's the Earth. Then you'll have the Earth's core is iron, and you'll have this molten iron, and the molten iron is churning around and moving around, and what you'll get is that you'll get these convection currents, and these convection currents will start to align the magnetic domains up, and you will get a noticeable magnetic field around this. And so, well, if you have your Fe core, then you're going to get a magnetic field around the Earth, and so we'll have our north and our south. And we'll have like this. And we'll have our arrows pointing from north to south. Like so. And so this would be the shape of the magnetic field around the Earth. And I've not talked to you about a definition for magnetic field strength at the moment, but well, let's do that. Well, magnetic field. So we would have magnetic field strength is referred to as magnetic induction. And so we call this magnetic induction, and the magnetic induction is denoted by the letter B. You may remember to higher, I was referring to the left and right hand rule as FBI. So force, the I was the current, B was the direction of the magnetic field, and so this is B, which is magnetic induction. And so magnetic induction, letter B, is measured in something called Teslas, named after the wonderful electric car. Not really. After Nikola Tesla, who did a lot of early work with electricity. So you have magnetic induction B, which is Teslas, and 1 Tesla is a huge quantity. It's very, very big. If you think about your standard bar magnets and the bar magnets that we'll have in our lab, they'll be in the order of magnitude of about a millitesla. If you're talking about the Earth's magnetic field, so the magnetic induction of the Earth is somewhere in the region of, I don't know, it's about 20 to 60 microteslas. And so that's really, really tiny. It's a millionth of a Tesla is the strength of the Earth's magnetic field. As another interesting thing, you should remember as well from higher about the so charged particles moving in magnetic fields, and so if you have, I'm not going to attempt to do this in a video, but you should remember your left and right hand rules, that if you have a charged particle coming into a magnetic field, and I think Mr. Forward does this in the quanta part of his thing, is about the aurora, and looking at charged particles as they enter the Earth's atmosphere, or the magnetic field of the Earth. And then what will happen is if they cross in perpendicular or with components perpendicular to the magnetic field, then you'll have, then they'll generally be deflected out. But what happens is that because as you get towards the north and south poles, then the magnetic fields are going to be coming in at right angles to the surface of the Earth. And so if a charged particle enters that's parallel to the field, it won't be affected. And so these charged particles can enter the Earth's atmosphere at the poles. And then as these charged particles come into the Earth's atmosphere, then they'll start interacting with the oxygen and the nitrogen in the atmosphere, and you'll get these lovely, you get these aurora in the northern hemisphere, aurora borealis, and then in the southern hemisphere we would call it the aurora australis, and you get these lovely wavy greeny patterns in the atmosphere. And so finally, we'll look at this last one. I compare the gravitational, electrostatic, magnetic and nuclear forces in terms of their relative strength and range. And on page 27 of the course notes, you'll see there's a few tables. But this one, the top one in particular, this is looking at the strength of the different fields or the different fundamental forces, I guess, that we would have. And so you can see here that strong nuclear and weak nuclear forces, they're the sort of subatomic forces. They're the forces that would act only over a very, very short range. But then our two, so we'll have our nuclear forces here, and then we'll have our gravitational and then our electrostatic and magnetic forces. And you can see, if we're talking about relative magnitude or relative strength of these, that these are all roughly within the sort of same few orders of magnitude. And so if you're looking at nuclear forces at between 1 to 1 times 10 to the minus 5 for nuclear forces and our electromagnetic forces, but a gravitational force is way, way weaker than this. If we were to look at an example of this, and going back to my my screwdriver bits, that if we have our screwdriver bit here, then it's obviously sitting on the page there because the mass of an entire planet is creating a gravitational field to pull it downwards. Yet the tiny magnet in the end of the screwdriver is enough to overcome the magnetic field of an entire planet. And so relative strength is that the nuclear forces and electromagnetic forces are very much larger and of a sort of similar magnitude to gravitational forces that are exceptionally tiny. I mean, it's like 1 times 10 to the minus 38 as opposed to the rest. Range. Well, the range would be, obviously your nuclear forces are internuclear, and so they will really only act within the realms of sort of atoms. Whereas electromagnetic and gravitational fields will extend, in theory, out to infinity. So they are much, much further and wider spread. Okay, so that's the sort of introduction to magnetism, and then thanks for watching, and I'll see you again soon. Okay, bye.